So let us start our discussion with exercise 8. In it, we have to check that the relation we saw in example 7 is really an ordered relation. Now, if I am remembering correctly, we already did this. If not, then this follows from the next one. Follows from the next one in the sense that whatever we are going to do here, this also can be verified exactly similarly. Okay, so in this next one, in the ninth one, we have to check that the dictionary order is really an ordered relation. So let's see the solution. Let A and B be sets with ordered relations on them. To distinguish the ordered relations, we write them like this. This is an ordered relation on A and this is one on B. Respectively. And let this be the dictionary order on their Cartesian product. Okay. So to prove that this is an ordered relation, we have to show our three things. We need to show that this relation satisfies comparability, then non-reflexivity, and then transitivity. Comparability means that if we take any two distinct elements, say x and y, simply I am saying x and y are two distinct elements of this Cartesian product, then either x should be less than y or y should be less than x. Less than I am saying just because it's easier to speak in like that, okay, in that term. But less than does not, of course, really mean less than in our ordinary sense. So let's consider two distinct elements. Let x naught times y naught. You remember that we have already decided to denote the ordered pairs in a Cartesian product like this, and x1 times y1, and accordingly we will call such symbols also like that, x1 times y1 be two distinct elements in A times B. Now these two ordered pairs can be distinct in quite a few ways. For example, you may have x naught different from x1, or you may have y naught different from y1, or both of them. Okay, so there are a few ways in which they can be distinct. If x naught and x1 are distinct, okay, then either x naught is related to x1 in this way or in this way. Why? Well, x naught and x1 are both elements in A, and this is already an ordered relation on A. So this relation also satisfies that comparability property. So you will have either this or this. If this is the case, then by the definition of dictionary order, this ordered pair will be less than this ordered pair. On the other hand, if this is true, then the opposite will be true, again by the definition of dictionary order. Okay, so that means if x0 and x1 are distinct, then really in one way or another these two ordered pairs really are related to each other. Now let's consider the other case where x0 and x1 are not distinct, they are the same. Next, let this be the case. However, the chosen ordered pairs are distinct. So to maintain that distinctness, now that we have these two things equal, y0 should not be equal to y1, because otherwise they will be the same thing. Then this is not equal to y1. These two elements, however, belong to B, and we have this order relation on B, which will also satisfy the comparability property. So either y0 will be less than y1 or y1 will be less than y0. If y0 is less than y1, then again by the definition of ordered relation, you see the first components of these two ordered pairs are equal and y0 is less than y1 in the ordered set B. Then this is again less than this. However, if I need to change this ink actually, it's giving me a little problem. Okay, I will change it tomorrow. So on the other hand, if this is true, then again by the definition of dictionary order we have this. So we have proved that no matter what the case is, these two distinct ordered pairs really are related in one way or another. So that means this satisfies comparability. Next comes non-reflexivity. Let me do it in the next another paragraph. So here we have to prove that, say, this ordered pair is not related to itself. What can possibly go wrong if I forcefully suppose that it is in fact related to itself? Let's see. Then, by the definition of dictionary order, either we have this or this is x0 is equal to x0 and y0 is less than y0. However, none of these two conditions can be true. Why? Because these individual orders on A and B themselves are non-reflexive. So, they do not relate any element to itself. So, this is impossible, This is also impossible, since this and this are non-reflexive. None of the above two conditions is true. So, that means we have run out of options. We cannot salvage our situation if we keep this supposition. So that means the supposition has to be false. Hence, this itself is non-reflexive. And lastly, we are going for transitivity. Let such that x naught times y naught is less than x1 times y1, which itself is less than x2 times y2. Yeah, now I remember that we actually really verified that the relation in example 7 is an ordered relation, because what we are doing here will be exactly similar. We have already done this, not this one but that one. So, either x naught is less than y naught, or x naught is equal to, oh sorry, what am I writing? x1, sorry about that. X naught is equal to x1 and y naught is, this is b, less than y1. So this is what we are getting from this relation, and a similar one from that relation. And either x1 is less than x2, or x1 is equal to x2 and y1 is less than y2. Now I think you remembered what we did in example 7. These possibilities give rise to 4 cases, and in each of those cases you can prove that x naught times y naught is less than x2 times y2. So I won't do anything more than this. So that means I am leaving it here. So what you now have to do, you go back to the verification in example 7. You see that video, and there you will see that those 4 cases are there. I mean, you do understand that we will have 4 cases, right? In one of those cases, we have this and this. In another one, we have this and this. In the third one we have this, and in the fourth one this and this. Okay, so the rest is left to you. I mean, it's almost identical to what we did there. So I am leaving this unfinished here. Let us now go to the 10th one. It has two parts. First of all, we have to show that the map from open interval -1, 1 to R of example 9 is order preserving. This thing is more sticky, it's stickier than the previous one. That is why probably you cannot see, but light smudges are there. So let's solve this one first and then we will see part B. We need to also recall what this function was. From example 9, we have this. So this was x divided by 1 minus x squared. Alright, now we have to prove that this is order preserving. This means that if I take 2 points x1 and x2, two real numbers from here, and say x1 is less than x2, then I have to prove that f of x1 is also less than f of x2. In general, I just have to show that f of x1 is less than or equal to f of x2, but here it turns out that it will be strictly less. Okay. So accordingly, let us choose 2 points x1 and x2 like this. Alright. What does it mean? It means besides the fact that x1 is less than x2, it also means that both of them lie here. Now lying here means what? Then their absolute values are both less than 1. You know that this inequality is equivalent to these inequalities, that -1 is less than x1 and x1 is less than 1. Similarly for this one. So this product, which from properties of absolute values is equal to this, that is also less than 1, right? Now what do we do with this? This implies now I am going to write something and then I will explain. Okay. 1 plus x1 x2 is greater than 0. How? Why? And how does this follow from this fact? Well, you see, there are two possibilities, right? Well, there actually is another one also. There are three possibilities. x1, x2 as a real number, not plus 1, okay, just x1, x2 as a real number is either positive or negative or 0. If it is 0, then this is equal to 1, which is positive. If it is positive, then also this is actually greater than 1, still positive. But if this is negative, if x1, x2 is negative, you look at this, okay, the absolute value of x1, x2 is less than 1. If x1, x2 is negative, by the definition of absolute value, what will be this? Minus of x1, x2. So that is why adding x1, x2 to both sides, you get this. This means that regardless of the sign of x1, x2, or even when it is 0, this 1 plus x1, x2 is always positive. Okay. We get another thing from this middle inequality. You see, so far we have only used this inequality and this other one, but now we are going to use the middle one also. The middle one tells us that x2 minus x1 is also positive. So we can multiply these two positive real numbers and still get a positive real number. That is, this times this is a positive real number. Now let me do the multiplication actually. So if I multiply by x2 using distributive class, usual stuff, then I get x2 plus x1 x2 squared, and then by minus x1 minus x1 squared x2, this is greater than 0. Now I will transfer two terms on to that side. Let me keep x2, this first term, and this last term on this side. That means x2 minus x1 square x2, and transfer the middle two terms to that side. That will give me x1 minus x1 x2 square. So the left hand side of this inequality becomes x2 times 1 minus x1 square, and the right hand side is x1 times 1 minus x2 squared. Now we are almost there. We now just have to divide both sides by 1 minus x1 squared times 1 minus x2 squared. But the question is, can we do that? First of all, you see, division will be possible provided that these quantities, these real numbers, are not equal to 0. Then only you can divide. Is it possible for 1 minus x1 square to be equal to 0? Well, in general, of course, it's possible. Precisely when x1 is either 1 or minus 1. Is that possible? X1 actually is greater than minus 1. It's never equal to minus 1. Also, it cannot be equal to 1. So 1 minus x1 square really is not equal to 0. But something more is true. not only is this non-zero, but it's actually positive. Why? Because if you square both sides of this inequality, on this side you will get absolute value of x1 square. On that side you just have 1 square, which is 1. But absolute value of x1 square is just x1 square by properties of absolute value. So you get the inequality that x1 square is less than 1. So 1 minus x1 square is greater than 0. Similarly, 1 minus x2 square is also greater than 0. Because of this positive nature of these things, when we divide, which we can because they are non-zero, inequality will not get reversed because we are dividing by positive real numbers. And if you actually do the division, you will end up getting this. Now you look at the function definition. This is f of x2 and that is f of x1, which means that if we write one more step, we are getting this. So yes, f really is order preserving. If x1 is less than x2, then f of x1 is also less than f of x2. So f is order preserving. Next we see part B. You may wonder how one can come up with these steps. Well, that's actually easy. See, whenever we write something as a solution, of course, we do not do back calculation within a formal solution. We just write whatever we need to write, and that should ultimately lead us to the solution. However, when we try to find the solution, when we try to find what to write, what to do, we start with this and then go in the reverse direction. So after playing with these things a little bit, you may end up with this situation, and then your job is to see whether this is true, and then you can find, this, you want this to be positive, this also to be positive, this is already positive, and that's why you want this to be also positive, and then your job would be to look for ways of showing how this is positive. And then you may think, okay, so x1 and x2 satisfy these inequalities. After some time you may get the other things that we have above this. Okay, so that way, and then you write in the reverse direction, that is the solution. So when you look at a solution, it may look magical, but it's really not that magical. So once you understand that this is how it is found, then part B. Show that the function g from R to this open interval okay, so it is phrased a little differently, but same meaning. I can write like this: defined by this. Is both a left inverse and a right inverse of the function f. whenever a function is defined, whenever a function is given to you, uh, it is well defined. I mean, people do not just give you blindly some relation which may not actually be a function and then ask you to do something with it. So, you can rest assured that this is a well defined function because the author has asked us to show that it is something, okay, it is this and this. But still, for our own satisfaction, we should really see that it's well defined. And I argue that that should actually be a part of the solution, namely showing that it's well defined, unless it's immediately clear that it is well defined. I mean, one thing about this G is of course clear. If I take any real number y, any y from the set of real numbers, and I put that y here in this formula, do I run into any problem? Is there anything happening like I have 0 denominator or I am getting a negative number inside square root sign? If no such problem is present, then it's okay. Okay in the sense that this output will also be a real number. Is that the case? Let us first of all see if 1 plus 4y square can be negative because it's under the square root sign. No, it cannot be negative. That is why there is no problem with this one. And then the next thing is to see if the denominator can be 0. That is also not possible. In fact, the denominator is positive and greater than 1 in fact. So, there is no problem with this formula itself. Once you choose a real number y, this is again a unique real number. But still there is one more thing you have to see. Is this output lying inside this interval? If not, then again this is no longer a function. So we need to at least verify that. And the way to verify that again involves some calculations which at first will seem arbitrary but later on will start to be meaningful. So we start like this. For any real number y, we start with this inequality. 2 plus 2 times square root of 1 plus 4y squared of course is positive. Right. There is no possibility of this ever being negative. 2 is positive, 2 is positive, and this square root by definition is the positive square root of something. That something is 1 plus 4y square. Okay, so this is positive. Now what we do? We add 4y square to both sides, which we can do by laws of inequality. And in that also, we split this 2 into 2 ones. We write one separately and with another one we write that 4y square. This of course remains the same. So we have added 4y square to the left hand side, so we should also add 1 to the right hand side. Alright. Now note carefully that this is 1 plus square plus 2 times 1 times. That means we are creating a perfect square. That's what it is. Now in place of y you can of course write mod y because there is a square. Okay. So the left hand side is now a perfect square expression. It is 1 plus square root of 1 plus 4y square whole square greater than this. Now we can take square root on both sides and the inequality will remain so, because the real numbers under the square, I mean the real numbers which you are squaring themselves are non-negative. That is, this 1 plus square root of 1 plus 4y square is non-negative, actually positive, and this 2 times mod y is also non-negative. But why do we need that actually? Why do we insist that we should have something positive or at least 0 when lifting square from both sides of an inequality? What can go wrong if that is not the case? Let me show you one thing. Yes. Is this true? This is true, right? Because this side is 9 and this side is 4. But note that the numbers that we are squaring are not both positive. This one is minus 3. Still the inequality is true, I mean this inequality is true. Now if I blindly, without caring for the signs of these bases, lift the squares, what shall I get? I will get this, but this is not true. That is why we should be careful about the signs of the bases. Okay, they should be positive. And that is why we have written mod y here, and we are not just simply blindly going to lift this square and write y. That would be wrong. Here also, if someone writes this instead, then it will be okay. Okay, so now we can lift the squares and have this. Or if I rewrite this inequality slightly differently, I am getting this. Now we have already noted that this is a positive real number. That means I can divide both sides of this inequality by this. What will that give me? 2 times absolute value of y divided by this. And that side will now become 1. Now you see, this denominator is already positive, 2 is already positive, but with y we have modulus, absolute value. So by properties of absolute value, we have this. This is less than 1. But what is this? This is g of y. So that means the absolute value of g of y is less than 1. Now in place of this inequality, you can instead write 2 inequalities and no absolute value. That is, we can write these inequalities. So, g of y, really the outputs lie between -1 and 1, and that too strictly without being equal to any one of them. And now we can say for sure that yes, g is a well-defined function. So now we come to the actual part of our solution. We now have to prove that G is a left inverse as well as a right inverse of the function f. What does that mean? Let us see the functions f and g a little bit more closely. This is what function f does. It takes us from this set to this set. G does the opposite. So what can I say about the composition G composition f? Because we have decided to write a function argument to the right of the function, that is we will write G composition f of x. We do not write x on this side. So that means we first apply f to x and on that we then apply G. So f is applied first. So that means this composition first takes me from here to this set, and then after that when you apply G, you go from this set back to that set. So G composition f is a function of this type, but you can also think of f composition G, which if you think like this will be a function from R into R. To say that G is a left inverse of f means that if you multiply, let me think of composition as a kind of multiplication. If you multiply f from the left by G, you are getting the identity function from this set to itself. If that happens, then we say that G is a left inverse of f. On the other hand, if you multiply f from the right side by G and you get the identity function from R to R, then we say that G is a right inverse of f. So we have been asked to show both of these things. So I will show one. What is it that you have to show here? You take any y. Let me just show that this is an identity function. This is the identity function from R to R. So you take any y in R. On that you first apply G, and then on G of y you apply f. You should get back y. If that happens, then this is the identity function from R to R, and that would tell you that G is a right inverse of f. What I said moments ago now about multiplying a function, about interpreting composition as multiplication, this interpretation comes from your group theory. Okay, now for any y belonging to R, so we are now going to calculate this. If you are doubtful, means if you are a little confused about what type of functions these compositions are, wherever you are doing these calculations alongside in a small space, you write like this. That will make everything absolutely clear. Now we know that we need to take y from R if we are considering this composition. Okay, so by definition this is f of g of y. Now what is g of y? This is 2y divided by that thing. F of this. But what is f? It may be a little big, okay, do not get afraid. So f divides the input by 1 minus square of the input. So the input itself is this. I just wrote this a little too big. Square. And this, of course, after this point it's simply algebra. So I am not going to show that calculation. Instead, that part I am leaving to you because it's just a routine calculation, maybe a little big. Dot dot dot. I want you to actually see for yourself that you really get y. And that proves, see, we have taken y as any real number. This means that no matter what y you choose, applying f composition g on y gives you back y if you believe that this is true. So, and then you can write f composition g is the identity function on R. On R means automatically it means from R to R. Thus, G is a right inverse of F. Okay, so your job now is to do the missing steps. And another thing, you have to also calculate G composition F on any real number coming from this interval and show that then you get x back. That will prove that G composition F is also the identity function, but this time on this set. So that will prove that G is a left inverse of F. That will complete the solution. Okay, so please do these things. And let me just end the video here itself. And tomorrow we are going to start complex numbers in class 11 mathematics. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.